right, so we're back with the class 11, and here is the example I wanted to do. I picked, I think it's 651, essentially. I think so. I'm not sure. I might have changed it. This was already partially covered in class 7 for the static case. So we're using that same piece. So a lot of this, you can go back to class 7 and check out a little bit of this. So here's what the loads look like. Let's see, it said they were putting 250 pounds on and off, right? Let's see where it says up above. The force F is applied as a repeated load, right? So just like that previous example, it's taken on, it's taken off, but now we're going to do it as fatigue load, right? So here I've graphed the thing out. Let's see. The free body diagrams might be necessary, so I think they've been skipped here, but don't do it because this is a simple problem. Don't usually skip out. But you could find what the torque is going to be. Is going to be the moment about x, because we have this force y that's coming up, and so it's going to be a maximum of 3,000 inch-pounds. And then the moment about the z-axis, which is going to be bending, so it's going to become like the top of right here, the top of this little juncture. About the z-axis is 2,750, and of course they're close to each other because there's 250 at once times 12, then there's times 11. So it's repeated, so that means that the alternating and mid-range are going to be equal to each other, and they're going to be equal to 1/2 of the maximum, right? So up here you could see that as the 1/2 of that force right there is going to be the average, and that's going to be the mid-range is right up to there, but it's also the alternating is right up there. And the same thing true for both the bending and the shear. So these are what the nominal before the stress concentrations are applied stresses will be. And the stress concentration, probably we could look this up from the previous use of this, that we get 1.39 in shear and 1.6 in the bending from here, from these two graphs right there. We can find a notch sensitivity. We have both a regular one and a shear one. And there is an equation for this, but it's a longish equation, so it might be worthwhile going with the figures. Right here and right there is approximately where I get the 0.78, I believe. Yes, see right just below, and right here for the shear, and we have to do kind of a little guesstimation of whereabouts the ultimate strength is for there. Boom, we can see that's just a little bit above 0.8. Okay, so they agree, and now we can apply those notch sensitivities to this to get like 1.47 here and 1.32, and now we can get these fatigue stresses. Now we've turned okay, so with these, I'm thinking this is just is this just a reminder? I think it's just a reminder. Now we plug them into the equations with the stress concentrations in there, and I end up getting 27 KSI with 2 decimal places of zeros. That's just a coincidence. KSI for these stress loads. So we want to take and find the endurance strength. We need to do that still. So we go through our process here. Notably that K1 is equal to 1, right? That's the important part here. So only 2 things that we really have are the surface factor and the size factor. Remember, this is, even though it's round, it is not rotating. So we do get an equivalent diameter for that. No temperature effects, no reliability, no miscellaneous. So we end up get 28.1 KSI, which if just looking at the alternating and this, we can see, well, we're pretty close with 27 and 28. So we can proceed and with our safety factors, and we can check out Langer. Notably, we get 1, but this is conservative, right? So we remember that. I think I actually, okay, so here I do take a step a side journey here and say, well, what would be the maximum, right? Even if I were to include the stress concentrations, I believe this is correct, we'd get 38.54. So this is actually what the yield safety factor would be, without doing that, adding the two together right there. So this is a demonstration that we're being overly conservative by just adding sigma A prime and sigma M prime to each other. So anyway, continuing on, here's the fatigue assessment. I didn't bother with the Soderberg. Let's just look at Goodman. And we can see 0.72, sure enough, predicts it'll fail. But even if you look in the denominator here, you saw 27 out of 28. So that's just a little bit below 1. And then you say, 27 compared to 64. And then you add the two things together. So just conceptually, what we're doing is the apples to apples comparison. We're measuring fatigue. We're comparing fatigue, and we're comparing static stuff, and we're saying, okay, here's the overall contribution from each of those. And then we could go backwards. We could see what the equivalent completely reversed stress would be, and we're predicting by the way of equation here, it's 46.7. We could also predict it by way of graph. By the way, this is a low strength thing, 64 KSI ultimate strength. So we're below the 70 that's at the far left of this figure 618. And if you read below there, it says use 0.9 in that case. So we use 0.9 to come up with these A and B, which are the coefficient and the exponents for our life equation. And we're able to plug it in and stick in the equivalent 46.7 that we found from this Goodman equation. We put him in, and now we have a prediction of 7,500 cycles. And that's our main goal through this, is to establish, does it ever die? And if it does die, when will it die? And there is a graph of that. And you could even see, you see that we got a Langer equal to 1. This is why. But also, because this is an on-off type of loading, we see that the load line is a 45-degree angle right there. And that'll always be true, right? Because that means that the mid-range is equal to the alternating, and therefore it's a line like that. And we can also see where it would have passed through these other dots lines, even though we didn't do it. But right here, like we had like a 0.72. You can see that's where it crosses, and we can see the line. Our point is outside the Goodman envelope, and so that's what we have right there. Boom, and here's our 46.7. That's our equivalent, and there we are on the SN diagram with the 7,500. Boom, boom, right there. And here's another example. I will do that in another video. Ta-ta for now. 8 minutes.